Part 2. 10 more real exam-style questions for the 2026 Databricks Data Engineer Associate certification. Same rules as last time. Pause after each one, lock in your answer, and count your score. Question 1. 60 analysts hammer ad hoc SQL all day. Some queries finish in seconds, others run for minutes. Your 3 classic SQL warehouses are over-provisioned at night and under-provisioned at peak. You evaluate serverless SQL warehouses. Which statement is accurate? A. They scale automatically with query concurrency. Zero cluster sizing or node choices. Fully managed by Databricks. Start in under 2 seconds from pre-warmed pools, and you pay per query execution. B. You still configure min and max cluster counts, auto-suspend thresholds, and node instance types. Databricks only takes over OS patching and Spark upgrades. C. They borrow idle compute from all-purpose clusters already running in the workspace. Queries cost nothing extra, while interactive clusters are up. D. They're optimized for overnight batch SQL only. The shared multi-tenant pool makes them unsuitable for interactive daytime traffic. The answer is A. Serverless SQL warehouses remove every infrastructure decision. Databricks handles capacity, scaling, patching, and the entire VM lifecycle. Pre-warmed compute pools give you near instant startup, under 2 seconds. Scaling follows active query concurrency, and billing is granular to query execution. That directly kills both pain points, the over-provisioning at night and the queue at peak. Option B is just classic with extra steps. There's no borrowing from your all-purpose clusters. And spiky interactive BI traffic isn't a weakness. Question 2. A retailer runs a 2-tier stack. An S3 data lake for raw history, plus a proprietary warehouse for BI. Data scientists copy warehouse data back to S3 to train models. Governance policies live in both systems and drift apart. How does moving to the Databricks platform actually fix this? A. It converts warehouse tables to Parquet to cut licensing costs, but the relational warehouse stays for BI workloads. B. Unity Catalog runs as a sidecar next to the existing warehouse, syncing permissions bidirectionally every 15 minutes. C. A proprietary columnar format, 40% smaller than Parquet, makes it cheap for each team to keep its own copy of the data. D. All data lives in open Delta Lake format on your own cloud storage. SQL, machine learning, and streaming run on the same physical dataset, with no copies, and Unity Catalog governs it all in one place. Lock in your answer. The answer is D, and this is the whole Lakehouse pitch in one sentence. One copy of the data in open Delta Lake format on your cloud storage. SQL analytics, machine learning, and streaming all operate on that same physical dataset in place. So those warehouse-to-lake copy pipelines simply disappear. And Unity Catalog becomes the single governance layer. Fine-grained access control, audit logs, end-to-end lineage, defined once, enforced everywhere. Keeping the warehouse keeps the problem. There's no permission sync sidecar. And more copies in a proprietary format? That's the disease, not the cure. Question 3. In a Python notebook, you need 2 things. 1. Run a shell command to list files on the driver. 2. Execute a shared helper notebook, so its functions and variables land in your current scope. Which magic commands, and what's the placement rule? A. %bash for the shell, and %import for the helper. Both can sit anywhere inside a Python cell, as long as they're not the first statement. B. %sh for the shell. It runs on the driver only, and %run for the helper notebook. Each magic must be the first and only content of its own cell. C. %shell and %include, and %include accepts a parameter dictionary that becomes notebook widgets. D. %fsls replaces shell listing entirely, and %run works, but it can be combined freely with Python code in the same cell. The answer is B. %sh is the shell magic, and here's the detail the exam checks. It executes on the driver node only, not on the workers. %run executes the target notebook inline, importing its variables and functions straight into your current scope. And the placement rule, 1 magic command per cell, and it must be at the top of that cell. No burying it in the middle of Python code. %bash, %import, %shell, %include, none of those exist. And %fs is for dbfs utility commands, not arbitrary shell. Question 4. An autoloader streaming ingests from an S3 bucket, receiving about 500,000 new files per day. The team debates the default directory listing mode versus file notification mode. Which comparison is technically correct? A. The two modes are functionally equivalent in latency. The only difference is S3 API cost from list objects calls. B. File notification mode is Azure only, event grid plus queue storage. On AWS and GCP, directory listing is the only supported mechanism. C. Directory listing periodically calls list objects to find new files. Fine at moderate volume, but cost and latency grow with file count. File notification subscribes to cloud events, SNS plus SQS on AWS, event grid on Azure, HubSub on Google Cloud, for near real-time discovery at high volume. D. Directory listing is deprecated since runtime 14. All new streams use notifications automatically, whatever the setting. The answer is C. Think pull versus push. Directory listing pulls. Every microbatch enumerates the source directory with list objects calls, so cost and latency scale with how many files are sitting there. File notification pushes. Autoloader subscribes to cloud-native event services. That's SNS plus SQS on AWS. Event grid plus queue on Azure. PubSub on Google Cloud. New files announce themselves. At 500,000 files a day, notifications are the designed answer. And no, the modes differ fundamentally at scale. Every major cloud has an implementation, and directory listing is still the supported default. Question 5. In a Lakeflow Spark declarative pipeline, what's the real difference between a streaming table and a materialized view, and which should back your gold layer aggregations? A. They're functionally equivalent. Both process only new records incrementally. The difference is internal file layout. B. Streaming tables append new records incrementally using a persistent checkpoint, ideal for ingestion sources like autoloader. Materialized views recompute their full result from upstream state on each run, ideal for gold aggregations and joins. C. Streaming tables are right for everything. The optimizer automatically converts aggregations into incremental stateful streaming computations. D. Materialized views store nothing on disk. They're logical views evaluated at query time, so they always reflect the latest data. The answer is B. A streaming table is backed by a persistent checkpoint and appends only the new records on each run, built for append-oriented ingestion from autoloader or Kafka. A materialized view recomputes its full result from the current state of its upstream tables on each pipeline run. Exactly what aggregations, joins, and derived gold metrics need to stay correct when upstream logic or data changes. So gold aggregations go in materialized views. And despite the confusing name history, materialized views really are materialized. They're physically stored, not evaluated at query time. Question 6. 2 DDL needs for a product catalog delta table. Scenario 1. Create it only if it doesn't already exist. Empty is fine. Scenario 2. Later, replace the table structure entirely. Rename a column, add another. Atomically, old data gone, no manual drop. Which pair of statements? A. Create table product catalog if not exist, then alter table with replace columns. B. Create or replace table for scenario 1, then drop table if exists, followed by create table for scenario 2. C. Create table with a location path, then truncate plus add columns plus rename column. D. Create table if not exists, then create or replace table. The replace is a single atomic transaction. The answer is D. Create table if not exists is the idempotent creation. Run it 100 times, it silently does nothing when the table is already there. And create or replace table swaps in the new schema and drops the old data as one atomic delta transaction. No window where the table is missing, no manual drop needed. Watch the traps. If not exist, without the S, is a syntax error the exam loves to sneak in. And drop then create is 2 separate statements. Readers can hit the gap in between. That's exactly what create or replace exists to avoid. Question 7. A job over 500 million records takes 45 minutes. In the Spark UI Stages tab, 200 tasks, 199 finish in under 10 seconds each, but one runs for 38 minutes. The data is partitioned by country code. What's the diagnosis and the fix? A. The driver ran out of memory collecting results. A garbage collection pause delayed the final task's acknowledgement. Increased driver memory. B. A yarn misconfiguration scheduled all 200 tasks onto one executor, serializing the work. Fix the node manager memory settings. C. The shuffle service is throttling one partition's oversized shuffle files to respect cloud bandwidth quotas. Raise the transfer quota. D. A broadcast join fell back to sort merge mid-execution for one partition after the lookup table crossed the broadcast threshold. E. Classic data skew. One dominant country code landed most of the data in a single partition. Fix it with adaptive query execution skew handling, salting, or skew hints. The answer is E. One straggler task, while 199 siblings finish instantly. That is the textbook data skew signature. Burn it into your memory. Partition by country code, and one country, think US, can easily hold 60% of the rows. That single oversized partition gets processed by one lonely task while everyone else waits. The remedies: adaptive query execution skew join handling, salting the hotkey, or explicit skew hints. And the eliminations are quick. A driver GC pause wouldn't make one task run 38 minutes. One executor running everything would slow all the tasks. And there's no bandwidth quota throttling mechanism like that. Question 8. GitHub Actions for a Databricks asset bundle. On every pull request, check that the bundle YAML is valid and every referenced file exists without touching any workspace. On merge to main, deploy to prod. Which pair of commands? A. CI runs Databricks bundle plan. CD runs Databricks bundle apply. The Terraform pattern. B. CI runs Databricks bundle test with a dry run flag against a sandbox. CD runs Databricks bundle deploy with a confirm flag. C. CI runs Databricks bundle lint for static analysis. CD runs Databricks bundle release. D. CI runs Databricks bundle check to verify permissions. CD runs Databricks bundle push. E. CI runs Databricks bundle validate. Syntax, schema, and file references. No workspace connection. CD runs Databricks bundle deploy, targeting prod. The answer is E. Again, Databricks bundle validate checks YAML syntax, schema compliance, variable references, and file existence, all without a single API call to any workspace. Exactly what a pull request gate needs. Then Databricks bundle deploy with target prod uploads the artifacts, resolves the production variables, and creates or updates every defined resource. Here's the fun part. The other 4 pairs are all invented. Plan and apply. That's Terraform's vocabulary, not the bundle CLI. Test, dry run, confirm, lint, release, check, push. None of those subcommands exist. If you remembered just 2 real commands, validate and deploy. Question 9. You're migrating a Hive metastore to Unity Catalog. Dataset A, Silver Delta tables produced and read only by Databricks. Dataset B, raw CSV and Parquet files that an on-premises ETL system writes straight to S3. Databricks only reads them. You propose A becomes managed, B becomes external. Which statement about the table types is correct? A. Managed tables are always Delta, and Unity Catalog owns the full lifecycle. Drop table deletes the metadata and the files. For dataset B, an external table means drop only deregisters the metadata, leaving the upstream systems files untouched. B. External tables give Databricks and the on-premises system full simultaneous read-write access, with coordinated transactions across both. C. After registration, the 2 types behave identically. Same formats, same drop table semantics. Metadata-only removal for both. D. Dataset D should be managed. Managed tables get predictive optimization and automatic clustering, so read-only data always performs better there. The answer is A, and this is the distinction between managed and external tables. A managed table in Unity Catalog is always Delta format, and Unity Catalog owns its entire lifecycle. So drop table permanently deletes both the metadata and the physical data files from cloud storage. Gone. An external table just registers files living at a location you control. Drop table only removes the registration, and the files stay put. Dataset B's files belong to that upstream ETL system. Imagine a managed drop wiping out another team's landing files. That's why upstream-owned raw data goes external, always. And no, external tables don't coordinate transactions with outside writers, and raw CSV written by another system can't be a managed table anyway. Question 10. Last one. The compliance officer asks 3 things. Where do Unity Catalog audit logs live, and how are they queried? What events do they capture? And can non-admin users get access? Which answer is right on all 3? A. Logs are delivered to a customer S3 or ADLS bucket, configured by an account admin under log delivery, then queried with external tools. B. Logs live inside the Metastore's internal store, retrievable only through describe history per table, or a REST API endpoint. C. Logs are built-in system tables, system.access.audit, queryable with plain SQL from any Unity Catalog workspace. They capture data access, admin actions, sharing, and job events. And admins can grant non-admins access to the system schemas. D. Logs land in an auto-created Databricks audit catalog, with daily partitioned event tables per workspace. The answer is C. Unity Catalog audit logs are system tables, system.access.audit, in the system catalog, and you query them with plain old SQL from any Unity Catalog workspace. They capture a broad range of events: data access, admin actions, Delta sharing activity, cluster and job events. And access is grantable. Admins can grant non-admin users read on the system schemas, so your compliance team can self-serve. The bucket delivery answer is the legacy path. Describe history is per table Delta history, a completely different thing. And there's no auto-created audit catalog. And that's all 10. Count your score. 8 or more? You're ready for the real thing. Tell me your score in the comments. And if you missed part 1, go take that quiz too. When you want full-length practice exams for this certification, they're waiting for you at testlogichub.com.